So let's look at some limits of composite functions. So the limit of a composition is the composition of the limits, provided the outside function is continuous at the limit of the inside function. So let's take a look at a couple examples. So here we have the limit of x approaches 0 of x squared plus 4. All right, so if I plug in 0, I get 4. We're going to call that g of x. All right, so the limit of g of x as x approaches 0 is 4. And I have another function, the limit as x approaches 4. Notice that the limit for the inside function becomes the input for the outside function. All right, so now the limit was 4, so the limit of f of x as x approaches 4, if I plug that one in, I get square root of 4, or 2. All right, so here at the bottom, so since the limit of g of x is x, that's weird, it moved. The limit of g of x as x approaches 0 is 4, and the limit of f of x as x approaches 4, right, as some value, is 2. The limit of our composite function, so the outside function, this would be the limit as x approaches 0 of the inside function was a g of x, f of g of x would be equal to, it's going to be equal to 2. And let's check. All right, so we would have 0 squared plus 4, which is the square root of 4, or 2. Right? So we can break up a composite, right, and do the inside function and plug that into the outside function. Sometimes it's easier for certain problems, but remember where we knew the values of the functions, but we didn't know the function, right? We can find the limits of composites the same way by using our properties. So back a few pages, right, where we had this. Pass that, pass that. This right here, right? So we knew the values of the limits, but we don't know the functions, right? So that's when another example when that property for composite functions would be very helpful when we don't have a function. Let's take a look at a couple more. Also just gives you another way to find the limit for a composite function. All right, so here we have the limit as x approaches 3 of 2x squared minus 10. Right, that would be 2 times 3 squared minus 10. All right, so that's going to be 18 minus 10, or 8. And notice the limit for the inside function becomes the composite function, right? The value of the inside becomes the input for the outside. So, and that extends to a lot of other classes besides just calculus. All right, so the limit of the cube root of x as x approaches 8 is equal to the cube root of 8, or 2. So notice that the limit as x approaches 3 of f of x is 8, and the limit of g of x as x approaches 8 is 2. That means that the limit and this will always work out, the limit as x approaches 3 of, so we'll call this one f of x, and u g of x. All right, so this is g of f of x is also 2. And that's because our function, our outside function, is continuous at the limit of our inside function. All right, so this will be true all the time. So you can do it, if you have, you break it up, or you can put it together again as a composite function. All right, so let's look at the examples in your notes. The limit of a composite is the composition of the limits, provided the outside function is continuous at the limit of the inside function. All right, so f of x is 4x minus 6, and g of x is equal to the square root of x. All right, so we work with our inside function first. All right, so we're going to find the limit of f of x as x approaches 5.5. All right, so that's going to be equal to 4 times 5.5, so linear, we can use direct substitution. So it's coming up very slowly, minus 6, which is, all right, so this would be 22, right, because 4 times 5 would be 20. 22 minus 6, which actually works out to be a nice number for the outside function, which is 16. Come on. And if we take the limit of g of x as x approaches 16, notice it's not 5.5, right? Because we evaluated the inside function first, right? So it's going to be the limit at this value for the composite. And that would be the square root of 16, which is 4. We're going to get the same value as if we did this as a composite function. So if I do this again, I'm going to do the limit. Come on, any day now. As x approaches 5.5, I shouldn't write up at the top. Look what I did to my arrow. Of g of f of x. So that's going to be the limit as x approaches 5.5. So f of x is the inside. So it's the square root of 4x minus 6, which would give us, now we'll do the substitution, the square root of 4 times 5.5 minus 6, which is the square root of 22 minus 6, that's 16, which is 4. So notice that the limit of the composite is the same as the limit of each of the different functions, but this here becomes the input for the outside function. So the limit of the inside becomes the input for the outside. All right, so when we don't have a function at all, you'll still be able to evaluate limits of composite functions. Here we have the limit of f of g of x as x approaches 5, 6 pi. All right, so now we're going to find f of x and g of x. So g of x is the inside function, and f of x is the outside function. So I'm going to do g of x first. So we have the limit of g of x as x approaches 5 pi 6. So that's going to be equal to sine 5 pi 6. All right, so let's draw that. Use our reference angle. So 5 pi 6, well 5, 6, that's more than a half, but it's less than a whole. Right? So it's in the second quadrant here because that's pi right there. All right, so, and this is 5 pi 6. So the difference between those gives me this angle here. So theta, which is, again, if I can draw it there, that smudge is theta. So theta here is going to be pi minus 5 pi 6. So that's going to be pi 6. That's our reference angle. Right? So pi 6, that's the same as 30 degrees. Right? It's a smaller angle in the 30, 60, 90. Right? And opposite is, this is, y is going to be positive, so this is going to be 1. Right? The adjacent would be the square root of 3, and that's negative. And then the hypotenuse would be 2. So sine of 5 pi 6, opposite over hypotenuse, that's going to be equal to 1/2. Right? And so the limit of f of x, because that was the outside, as x approaches 1/2 is equal to 2 times 1/2, or 1. Now let's see if we get the same with the composite. All right, so we have the limit of f of g of x as x approaches 5 pi 6. That's going to be equal to 2, that's the outside. I don't really need the parentheses. In this case, oops, need to put the pen down when I'm erasing. Board doesn't like that. So we have 2 sine x. All right, so that's going to be, if we plug in here, that's going to be 2, because sine is continuous everywhere, right? And 2x is continuous everywhere. So these are continuous functions. And these have to be continuous everywhere. So we have 2 sine of 5 pi 6, which we already know 5 pi 6 is 1/2. So that's 2 times 1/2, which is 1. All right, so 2 ways to find limits for compositions, for composite functions. Right? Hopefully this all made perfect sense to you, and you see how we're working with composite function. It's actually the same way you'd work with composite functions in other situations. Right? So if you're separating them, the input is the output from the inside function, because we plug into the inside first, and then we evaluate the outside function at whatever the inside function was equal to. That just applies to limits too. So evaluating limits, as with polynomials, limits of many familiar functions can be found by substitution at points where they are defined. This includes trigonometric functions, exponential and logarithmic functions, and composites of these functions. We'll look at trig functions in the next lesson. So the limit process, here we have an example, x squared minus f of x is equal to x squared minus 9, x minus 3. There we have it graphed. It graphs as a linear function, but notice it has a hole. So if we're letting c equal 3, notice that the function f is not defined at 3. Both the numerator and the denominator are equal to 0, but that doesn't matter. So x does not equal 3, and therefore for all x near 3, all right, we can find our limit. So as x gets closer and closer to 3, the limit, as we approach from the left-hand side and the right-hand side, is equal to 6. So the value of the function for x close to 3 is our limit. So the limit, and we're going to simplify this function to find it. So from the graph, we can see the limit of f of x as x approaches 3 equals 6. Let's simplify the function. So now we'll do it analytically. All right, so we have the limit of, as x approaches 3, x squared minus 9 is x plus 3, x minus 3 over x minus 3. Those would cancel. So we have the limit of, as x approaches 3, of x plus 3, and now we can substitute into this one. All right, so if we were rewriting the function, it would be if x is not equal to 3, but it's not important for the limit because we don't care about the value of the function, we just care what it's approaching from either side. So now we can substitute in because we've reduced it. We've eliminated the factor in the numerator and denominator that repeated. So now we would just have 3 plus 3, which is 6. So notice that the limit from the graph is equal to the limit we found analytically. I think I have just one more page, and it's a really simple one. It's just some easy, cheesy, lemon squeezy limits, right, using substitution. So the limit of 3x as x approaches 0, I can plug in, because I'm continuous there. That's 3 times 0, or 0. The limit of 5 times the square root of x minus 1 as x approaches 1. Now, interestingly, let's change up this question a little bit, and let's put a plus there. All right, so now from the positive side, all right, I can plug in 5 times the square root of 1 minus 1. So that's square root of 0 is 0. 5 times the square root of 0, that's just 0. So the right-hand limit is 0. And generally you'll see this question with the so it's specified right-hand limit, because the limit of 5 times the square root of x minus 1 as x approaches 1 from the negative side does not exist, because this is an endpoint. So 0 here is an endpoint, or not 0. 1 is an endpoint, because x was 1. That's the answer when we plug in 1. But, so 1 is an endpoint. So this is not a two-sided limit. This is a one-sided limit only. Tricky, tricky, you have to remember. So that's why I did it from the positive side, because it doesn't exist from the negative side. One-sided limit only. Let's look at the next one. All right, so we have the limit of 5x plus 1 divided by 2x minus 1 as x approaches 3. No problem with the denominator being equal to 0, so we'll just plug in. All right, so this is going to be 5 times 3 plus 1 divided by 2 times 3 minus 1. And by the way, you'll write the limit statement unless you literally have it written right there. And so this would be 15 plus 1, that's going to be 16. 6 minus 1 is going to be 5. And so that's it, 16/5. And then the last one there, the limit of x squared plus 5 as x approaches negative 2. Polynomials are continuous everywhere, so we can just plug in. You can just substitute. So that's going to be 4 plus 5, or 9. All right? So these are nice, friendly, well-behaved functions we can just substitute in. The only one that wasn't well-behaved was the radical function, because that was a one-sided limit. So you can do some whiteboard problems. Look how nice and easy that is. And I was kind. Notice my radicals are mostly one-sided limits. And so let's see how you do with these. All right, so we'll do these in class. And thanks for watching. Bye for now.